There we go. All right. Good morning, everybody. So last time we saw an example CPU. We built it by thinking about what's an abstraction that denotes a minimum amount of ability necessary to do arbitrary computation, the Turing machine. And we built a very simple CPU inspired by the idea of a Turing machine. Major theme was the idea that as an instruction comes into the CPU uses that instruction to determine what's going to change, right? So in effect, every machine language instruction is about a state change in memory. And that memory can be in several different forms or contexts, right? For example, we might be talking about RAM, and that's pretty common. But we also might be talking about the CPU's registers. We also might be talking about an output device. It could be any of those things, but fundamentally, every machine language instruction is changing something in the machine. If it's not changing anything, it can't do anything. There's nothing meaningful about that instruction having been executed unless something changes as a side effect of that instruction. At that point, we're actually getting somewhere. Thinking further about this then, an intrinsic part of the state change is thinking about the program counter. That is, part of the state we might change is simply deciding which instruction we're getting to next. Finally, we have to take into account the fact that there are inputs that affect what the instruction does. And it might be data that's already resident in RAM. It might also be something from an input device. In the case of the machine we're looking at here for this course, that device is principally the keyboard. But there are many other such devices that in principle could serve as influences on how an instruction changes the state of the machine. In thinking about the big picture of this then, what we recognize is that to build a CPU requires us to wire up all possible state changes. So as we're figuring out how to wire this CPU circuit, we have to hook it up to make possible every state change that the design of the machine implies. Whether or not those changes are actually propagated comes back around to the following ideas. First and foremost, the load input on our memory devices. So we've got all possible changes set up and wired, but we only permit them to happen if an aspect of our instruction causes the load input to go high on the element of the computer that we intend to change. So, an interesting side effect of this is if we've wired all of it up to make all changes possible, and we're not careful with the load inputs, then we're going to make all possible changes. And we saw examples of that last time when we were considering the distinction between an A instruction and a C instruction. With a C instruction, different bits enable different things to happen. With an A instruction, you're just loading an address. Well, if you're not careful to suppress the load bits when an A instruction happens, just loading an address can cause all kinds of bizarre state changes. So the load input, getting the load inputs right on your state elements is essential for building a CPU. Looking back at what those elements are, ultimately, we're just changing one of these things. from the CPU's point of view, RAM and output devices are literally the same thing. That is, by memory mapping our output device so that it looks like a location in RAM, and importantly, has an activating load bit, we find that from the CPU's point of view, these two just collapse into the same thing. Distinct is the notion of CPU registers. So CPU registers are essential for helping guide the CPU to actually do something. As we saw, for example, many instructions depend on the notion of an address. That is, where in memory, whether it be program memory for a jump or data memory for reads and writes, where in memory is this going to have an impact? In this CPU design, we need the A register in order to specify these things. Furthermore, we wind up having a lot of value in having this D register around. It's a nice place to temporarily park some data in the midst of performing a computation. Part of the reason we need it is if we didn't have the D register, we would certainly need two A registers so that we could be simultaneously specifying two distinct memory locations upon which a calculation is premised. So, yeah, it's 6 to 1, half to the other. You know, you get rid of the D register, you need another A register. You get rid of the idea of an A register, now you need really big instructions that actually include the addresses. But, you know, fundamentally, we just have to deal with that stuff. And then there's the all-important program counter. The program counter is fundamentally responsible for determining what is the next instruction. And the ability to control what is the next instruction is essential for anything we might even call a computer program to be worthy of the name. It's a big picture way of thinking about the CPU. Any questions thus far? Okay. So then last time, we actually, right here in class, designed a simple CPU. We came up with an instruction set, and we examined how those instruction bits contribute to decoding what the instruction's actually going to do. And what we saw is that these instruction bits got routed in a couple of different ways. First and foremost, instruction bits often got directly tied to load bits on an element where the state changes. Depending on what that instruction bit was, it determined whether we were changing the head register that was tracking the read-write head, the program counter, what have you. So that was one very important role of the idea of an instruction bit. Another important routing of instruction bits is for the select bits on multiplexers. So often we have multiple options for what value gets loaded into something that changes. And so when that happens, what we need is a multiplexer. And typically, the bits in the machine language instruction can be directly routed or sometimes mediated by a little more logic into the select input for a multiplexer that controls what might be coming in. And so that, too, is an essential aspect of instruction decoding right there. What are you going to change? What load bits go high? What thing goes into the thing that's changing? Select bits on a multiplexer. That all makes sense so far? All right, so having thought about this context, what we're going to do now, whoops, if I can actually not drop the book. Because you know what? I know it's early for you guys, and it's early for me too. But here we are. Here we are. So we're going to review what a machine language instruction actually constitutes in this hack CPU. So last time we were able to build a really simple kind of made up CPU. I'm obviously not going to show you all the details of how to do it for the hack machine, since that's, the assignment. But what I do want to do is review the 16 bits that constitute a hack instruction so that you can start putting together in your own minds how the architecture we looked at last time relates to the task that lies ahead of you now. All know where we're going? All right, cool. So let's review. So a hack instruction, as we've discussed many times, and as you internalized in the assignment where you wrote your assembly language programs, there are two types. And the first of which is the A instruction. So in an A instruction, you all flashing. All right. So in an A instruction, 16 bits wide, we always have a 0 in that leftmost bit. And then the other 15 bits represent an address. So this particular design decision on the part of the architecture designers, and when I say design decision, kind of back up for a minute and emphasize the importance here. Much of our discussion last time centered around the fact that we were trying to discern, where do these instructions come from, right? What's their source? What's their origin? And what I really wanted to emphasize, and I'll continue to emphasize, is that they're all a bunch of stuff that somebody just made up. If we decide that a particular architecture is going to have an A instruction and a C instruction, well, why is that the case? We made it up. Why is it that the signal in A instruction requires a 0 in bit 15? Because we made it up. We just invented it. We could have flipped it around. We could say, well, there has to be a 1 here and then a 0 for a C instruction. We could say, bit 7 in the middle is what distinguishes an A instruction and a C instruction. We can do that. You can build a CPU that way and it'll work. So what we're actually doing is trying to think about what kind of bit encoding is fundamentally most intuitive, right? What kind of bit encoding is easiest for us to understand as we're in the process of getting our work done? And that's really the heart of what we're attempting to do. So, in the case of an A instruction, part of the beauty of this scheme is that if you examine it as either a 15-bit value or a 16-bit value, when you convert that binary value to decimal, you get the same value. So there's a lot of benefit in that. It just makes the mental mapping between this instruction and what it's actually doing easier than if, say, we decided that the key thing was bit 7. I mean, we can do other crazy stuff too. Like we could say, well, it's like a binary number, but it's shuffled. So, the highest order bit is here, and then the next higher order bit is over here. And then the next one is over here, and then the next one is over here. And then here, and then here. Like, we could do that as CPU designers, as instruction set designers. We could decide that that's what an A instruction is. But we don't, because it's crazy, right? And what I mean by crazy is that we need to keep in mind that even something as opaque as a machine language instruction can always be worse. And it's just nuts to do that. So we look for a way to make as transparent as possible its meaning. Now, this has important implications for the design of the circuit. Namely, you're going to be accessing this instruction bit 15 a lot when thinking about your load bits and your select bits, especially the load bits, right? If this is a 0, the load bit on the A register needs to be a 1. And the load bit on essentially everything else is going to have to be a 0. And by doing that, you prevent lots of inadvertent state updates from happening. So I know from experience that when people are doing this assignment, a really common source of bugs is that when this is a 0 and it gets sent to a 1, some of the other load bits are still being activated, and then everybody's CPUs go nuts. And I've got students in my office wondering what the heck is going on here, and that's fine. If you've got problems, I want you in my office, and several of you have discovered that, which is excellent. But I think it's worth knowing ahead of time that that's an enormous source of trouble with the CPU design, is if you don't have the load bit set up correctly for the things where the state can change. Getting that right is 50% of the battle with the CPU. Cool. So that's the A instruction. Any question? Yeah, so then obviously bits 0 through 14 are going to be trying to go into the A register, but there are other things that can go in there. So there's going to be a multiplexer, right? Because we can have an ALU output also going to the A register. So it's important then to make sure that we're clear on the fact that there are these multiple possible sources for its value. With the A instruction then, this tells us both make sure you load the A register, and at the same time it tells that multiplexer make sure the thing going into the A register is the other bits from the instruction. Conversely, and we'll be talking about this in a moment, when we're thinking about resetting the A register based on an ALU output, we're going to have some kind of an OR between this bit and the C instruction bit saying, we're actually going to change, the A register. But then when we get to that point, that's going to have to influence the select bit on the multiplexer as well. So yeah, there's some complexity involved, more than we looked at on Tuesday. But the key theme is always be thinking about what's getting changed and what is the change. Knowing that a complete explanation of that is derivable from the instruction bits and possibly some other stuff in memory. So that's the A instruction and thinking about wiring that. Any questions thus far? Innocent, I'm feeling a question.
I am trying to see the best way to phrase it.
Go for it.
It's still fuzzy in my head.
No problem. Take a moment.
So you told us that, like CPU designers, maybe perhaps us, we chose to put a 0 there,
right?
Because it makes more sense since we can take that value, convert into a decimal,
yep,
and it still be the same thing because 0 is not going to change it.
Exactly. Yep.
Yeah. So, is it true to claim that this is probably the best way to do it that is out there?
It's the best way to do it, assuming that you take this distinction between A instruction and C instruction. So there are machine languages that don't make this distinction. In fact, almost all realistic ones.
So what else can they, what other assumptions can they make? Let's give us an example.
Right. So for instance, one assumption we're making in this architecture is that every instruction is the same size, one machine word. There's no intrinsic reason why you can't have an instruction that's 2 or 3 machine words, or 4 even. So, in other words, you can have variable length instructions. And part of the process of decoding the instructions, the CPU looks at the very first machine word that comes in. And based on the bits there, it might tell it, okay, you now need to look at the next word. This has a side effect that if you want to do it that way, executing an instruction that takes multiple words is going to take multiple CPU cycles. Yeah. It's kind of nice to have the notion of every instruction executes in one cycle, because it's a way to kind of keep things moving. So what do you do at that point? Well, what you could do is, say you've got a 32-bit instruction. You could say 16 bits will be the encoding for the ALU and everything. And then the other 16 bits are an address right there. And then you can build it right into the instruction. It's maybe a bit easier to conceptualize with a 64-bit instruction because 64 bits is a lot of options, right? Specifically 2 to the 64th, a value I have not memorized, for which I hope you'll forgive me. But at that point, it's pretty easy to see, okay, well, we could have, 24 bits, say, of instruction encoding and 40 bits of address. If you've got a 40-bit address bus, you have a lot of addresses. Bearing in mind that 2 to the 32nd power gets you to 4 billion. 2 to the 40th power is going to be a trillion, basically, yeah, roughly. So now you got options, right? So that's another way that one can think about building an instruction. So what's nice about that approach of a 64-bit wide instruction with the address built right in is now you can still do everything in one cycle. This is a really important subtlety in instruction set design. Whenever somebody's marketing a computer, they say, well, its cycle time is 3 gigahertz. But now you can also ask the question by examining the instruction set, how much work is it getting done in a clock cycle? And that too tells you something about the throughput of the device. I mean, certainly knowing the clock cycle tells you one thing. But if it turns out it's got a machine language that requires 6 cycles for an instruction, and you're comparing, so you got a 3 gigahertz machine, 6 cycles for an instruction. A 2 gigahertz machine, 2 cycles per instruction. The 2 gigahertz machine is actually going to be a faster machine, assuming that instructions in each one achieve the same amount of computation. So when people advertise it's this many gigahertz, it's telling you something, but it's also hand waving like crazy. That's okay. It's a nice sort of first order of approximation way of thinking about it, but it's definitely not the whole story. All right, so that was a bit of an aside, but an interesting one. Cool. Any other questions so far before we get to the C instructions? All right, C instructions then. So we're going to go over how the book specifies the C instruction. And we've done this before, but I think looking at this again from the standpoint of how am I going to wire this has a lot of value. So the high order bits are all ones. Notice that these 2 bits actually don't matter. Why would I say that? We can fully distinguish whether it's an A or a C instruction by looking at bit 15. The specification is, well, you should have ones there also, just because the instruction set designers are saying we don't want any undefined bits. We want every bit to have a defined setting to make it easier for a writer of an assembler to know what to do. That said, these 2 bits just don't matter. It's perfectly acceptable to have a CPU design where even if you had 2 zeros here or 1 0 or a 0 1, it still works exactly the same way. You definitely don't need to do something like say, well, to distinguish an A or a C instruction, I need to AND all 3 of these bits and make sure that they're ones. You could do that, but then what does it get you? Imagine the zeros or ones come in here. There's a bug in the assembler, say. Is it really necessary to make the CPU fail at that point? Well, no. It just doesn't matter. So your CPU doesn't really need to enforce anything about these. The instruction set design is simply promising the assembler writer if you've got these there, it'll be a C instruction. If you don't have these there, it's just not promising any particular behavior. But there's no particular incentive to make it misbehave if they're zeros. And so there we are. So this next bit is called the A bit. And the A bit is controlling the source of the second ALU input. Controls the source of the second ALU input. So on the extremely important page 67 of the book, there's this table describing the computations made by the CPU based on the next 6 bits, which we'll examine in a moment. Key insight is that it's got these 2 columns. It says when A equals 0, it does these things. When A equals 1, it does these other things. Specifically, when A equals 0, so when A is 0, the A register is that ALU input. When A is a 1, then the memory location referenced by the A register is the input. And that memory location is denoted M. Now, you no doubt remember this from when you were writing your solutions for project 4. But it's really worth talking about here because what we can see is that this A is going to be the select bit input for a multiplexer that has as concrete inputs the A register value and the value from RAM. This gets back to the theme that in a CPU, you're constantly trying to do everything. Everything that you're trying to do is the universe of everything that's possible to do. If you want a possibility, you have to wire it to actually be making it happen at all times. The select bits and the load bits then are the gatekeepers saying, this time, this is what we want. And so that, in turn, leads us to these guys. So these are the C bits, C1 up to C. I meant to write a C there. Let's try that again. C6. I was thinking 6 and writing it, but wanting to write C. So we got the 6 C bits, C1 through C6. So in thinking about this, I mentioned there's an extremely important chart on page 67. What I want you to do as part of this assignment is to compare this against the chart on page 37. That chart on page 37 was the specification of the various ALU calculations. So it's not really giving the game away to say we can take those 6 bits and feed them straight into the ALU. Yeah. I want you to look carefully at both of those charts, page 67 and page 37, to understand why you can do that. But in fact, you can. In fact, you should. The ALU was designed with this specific instruction set architecture in mind. It's intrinsic to the ALU. And so that's what enables you to do that. So those 6 bits are just going straight into the ALU. This is controlling an ALU input. So far, you might notice we haven't changed anything, right? We've routed 1 bit to decide on an ALU input, 6 more bits to tell the ALU what it's spitting out. The last 6 bits we haven't looked at yet are all about what changes. Every possible change to the CPU from a C instruction depends on these last 6 bits, each of which specifies either a different thing that changes or a condition in which it might change. So first, we're going to look at these guys, D1, D2, D3. So A stands for address, C stands for computation or calculation. D stands for destination. When we're thinking about a destination, that's where we're thinking about what's going to change. There are 3 destination bits, each of which with a 1 indicates this destination changes, and with a 0 indicates this destination does not change. So what are these mysterious destinations? Nothing mysterious at all, really, right? So thinking about the D bits, there's a nice chart on page 68 that indicates their meanings. So D1 means that you're changing the A register. D2 means that you're changing the D register. And D3 means you're changing memory. In other words, you're changing the value at the memory location that A is pointing at. So depending on the value for A, that determines which M gets changed. Now, it can be kind of mind-blowing to think about this. What if all 3 of them are 1s? Or what if both D1 and D3 are 1s? Then it's like, well, what happens? Is the M going to be referenced by the new value or the old value? What do you all think the answer is? Yeah.
So the question says, if D1 and D3 are all 1s, what's the value of M?
What is the memory location of M? Yeah. Andre, were you just stretching? So why would it be the new address? So this is a great question, which is actually getting to the heart of the issue, which is what is going to be the input to where we're writing in RAM? Is it what the A register had been outputting or what it's inputting? So here's a way to think about it. It goes back to how a RAM is implemented, how a D flip-flop is created. Let's review that and see what insight we get. So thinking back to the D flip-flop, you might remember that it consisted of 2 D latches, right? And so the loads on the D latches are wired to the CPU clock. So the clock goes through a NOT gate into that one and then just goes directly into that one, as you might remember. And then the output of this one goes into the input of that one, and then we've got this output over here. So let's think about what happens as the clock pulses. So whenever we're trying to store a value, it gets queued up in here, waiting for a clock pulse to move on to here. So what will happen is, as the clock pulses, imagine this is our A register, right? So our A register has an output that's going all the way in to the RAM chip to say this is the address we're playing with, okay? So that output going all the way there is what's queued up for when this clock pulse happens. What that means is that when we're thinking about which M are we looking at, it's going to be using this previous output of the A register. So it's what the A register was that's controlling what's getting updated, which location in memory. So then as that update happens, sure, A changes, but as A changes, the thing it's routed to is queuing up its new output. It actually used its old value. So in this situation, the M that's being referenced is the M referenced by what we'll call old A. Old A. But it's pretty confusing to think about this. Now, as you might have discovered in the previous assignment, it can sometimes be really useful to set A using an ALU calculation, and not just by using the A instruction. So for instance, if you've got a memory location that you're updating, that's a pointer to, say, a group of 16 pixels on the screen, for example. I don't know where I came up with that. Okay. By saying something like A equals M, we're able to say whatever that location is, just stuff that value straight into the A register, and now it's pointing at that. That can be really handy. So this is really useful stuff when thinking about this architecture. It can also be useful sometimes to simultaneously update two different values, like if you want to simultaneously update a memory location and have that value still be in the D register, the setting bits 2 and 3 to 1 and keeping 1 at a 0 can be really handy as well. I know in my solution, one of these, at some point I said something like MD equals M plus 1 or something like that when I was incrementing something. So this is really handy, really useful ability. Importantly, for our circuit design purposes, these three then are going to be connected, maybe mediated by some AND or OR gates or NOT gates, to load bits. These are deciding what gets stored. Note that these destinations are unconnected to the ALU inputs. So you can set A to be 0 or 1 however you want. You can actually then write to both A and M, either one, whichever. So the A bit over here has no effect on the destination. The A bit is strictly about what's going into the ALU. Everybody with me so far? All right. So it's a very limited number of things that change, right? A register, D register, and RAM. And RAM, of course, also includes the screen because of memory mapped I/O. So our last group of bits are the J bits. There's a very handy table on page 69 with reference to these J bits. So J1, J2, and J3. Now, unlike the situation with the D bits, all of the J bits are changing the same thing. What would that be? What's the thing whose state changes as a result of J bits? So what changes in a jump? The program counter, right? So all of these are about changing the program counter. So what these represent are the conditions under which the program counter actually changes, right? So J1 is if the output is less than 0, J2 is if it's equal to 0, and J3 is greater than 0. So to determine these, you're going to use the ZR and NG outputs of your ALU. So for each of these conditions in your circuit, you need to wire up when am I actually jumping. So for instance, if I want to jump on a less than 0, I both have to have this bit out of 1, and then I have to have my negative flag set. In other words, use an AND gate or whatever. And the same thing for this, and then greater than is a little more complicated. But you can certainly derive it knowing the 0 and the negative flags. Basically, if it's not a 0 and it's not a negative, it's a positive. Sadly, our ALU doesn't have a PS output, but it's really 6 of one, half a dozen of the other, right? You could have put that circuitry into the ALU and had an extra output and had an abstraction here, or you can just do it right here. And in this case, you're going to do it right here. So for each of these, you've got circuitry indicating, does this hold? Am I going to jump? And then in effect, you just OR them from there, because if any of these, if more than one of these is a 1, any of those conditions being a 1 is sufficient to cause a jump. And if you're going to cause a jump, it comes back to the PC, and it comes back to the all-important load bit that determines a jump. And we looked at that last time when we were looking at kind of our super made-up Turing machine CPU. All right, cool. So that's a C instruction. And at this point, you've pretty much nailed it, right? Now, there's a little more to the assignment than this. And the CPU is absolutely the heart of it, okay? But there is a little more to it than this. So if we look at the assignment, just want to clarify that these other parts are there. There's a chip called memory, and that chip consists of putting together a RAM 16K, the screen and the keyboard together, and using multiplexers and demultiplexers to do the memory mapping of the I/O. This memory chip then is going to be what our CPU is talking to. It won't be talking directly to the RAM 16K. And the reason, again, is memory mapped input-output. So then CPU.test is obviously the bulk of the points. That's getting your CPU working. Okay. Then there are 3 computer tests. So the computer chip is the memory and the CPU and the ROM, the program memory, all put together. That's the chip they call the computer. You can imagine that as, at that point, I've got my motherboard wired up. And once I've got my motherboard wired up, it's just a matter of physically plugging in my I/O devices right onto the motherboard. Obviously, in this era of USB and HDMI and the like, you know, we can just sort of plug things in and out. And what happens is the receptacle, the female side of the receptacle here is getting electrical connections between the pins in the male side of the connector lining up perfectly so as to complete the connection. It's plugged in that sense. And then on the receiving end, the female end, those are then just wired directly to the appropriate inputs on the motherboard. And so there we are. So these 3 tests will thoroughly determine that your computer integrated as a whole is functional. So, but obviously the single biggest, most important part is the CPU. The memory, that should be super easy. That's like 5-10 minutes. CPU, it's more than 5 or 10 minutes. The computer itself, maybe 15 minutes. Tops. Should be able to do it. If you're struggling, of course, just come on by. Any questions then on Project 5? Any questions? Yes, Andre. No, those were just made up for that architecture. For that idea of this Turing machine CPU. For this project, it's strictly what's enumerated here. Good question, good question. Any other questions on Project 5? Questions on Project 5? So as I go into this next part of the lecture, if any questions come to mind, feel free to interrupt me. And we'll just see where we're at. What I'm going to do for this next part is talk a bit about what we might think of as some more realistic CPUs and give you a feel, generally speaking, for what those instruction sets look like. I'm going to begin by talking a bit about some historical families of CPUs, of processors, and kind of trace out which CPUs have become popular at various times for various reasons. From there, time permitting, we might look at some concrete examples of what their instructions are like. So, in thinking about this, I'm going to start by thinking about the era of the desktop machine, the personal computer as it was called. Until the mid to late 70s, a computer was like a giant room-filling thing. It was huge, enormous. The idea of even a desktop machine was absurd at that time, to say nothing of something like a smartphone. Okay. So that was from the 40s through the start of the 60s. Okay. So 40s to early 60s, these mainframe, room filling CPU. Starting in the early 60s and influential perhaps to the late 70s or so is what is called a mini computer. And so a historical example of this would be something like the DEC VAX. When you think about mainframe, think early IBM. Actually, they still make them to this day. So the DEC VAX was a typical mini computer. So the idea of a mini computer was that it didn't fill a room anymore. Like a mini computer, this could be something like, cabinet sized. You could imagine it taking up a chunk of space on a wall in a room or something like that. Starting in the mid 70s is when we started having what's called a microcomputer. And these are the machines that you all are familiar with, is a microcomputer. And what distinguishes a microcomputer is the CPU is what's called a microprocessor. It was a CPU on a chip. And in the context of the time, this was astonishing. Absolutely astonishing. So let's talk about some of the microprocessors that were popular during this time. One was the Z80. That was made by the Zilog Corporation. Another popular CPU of that time was the 6502. Closely related to this was a family of processors from Motorola. 6502 was from MOS Technologies. Motorola included like the 6811 during this time period. All of these in this family were 8-bit CPUs for data, the 16-bit address bus. So instructions were 8 bits, arithmetic calculations made on board the CPU were 8 bits. But it could address up to 64K of memory. And so 16-bit address bus. So what are some characteristics of these CPUs? As it happens, I brought with me today this book entitled Programming the 6502. The reason I have this book is because the largest amount of machine language programming I ever did was on a 6502 family processor. And so I keep talking about it because it's deeply rooted in my childhood. And so one year there was a group of computer science seniors that as they graduated somehow found this book at some used book thing or maybe on Amazon and gave it to me as a farewell present, just so that every now and then I could take it down from the shelf and think about my childhood. So anyway, so I'm going to talk a little bit about what programming on the 6502 was like. So the 6502 had 5 registers, and this was fairly typical for all processors in this family. This was especially closely related to the Motorola family. I think I've referenced before how early in graduate school I was writing a device driver to control a pan-tilt motor on a robot. The processor I was using was a Motorola 68HC11, which was a special embedded controller version of that chip. And programming it was extremely similar to the 6502. So it had 5 registers. So what were these? It had, of course, a program counter. Then it had A, X, and Y registers, and then a register called SP. So program counter, I think we're all clear on a program counter. Okay. A register, A stood for accumulator, and its role was very similar to the D register in this hack machine that we're exploring now. X and Y were referred to as, whoops, let me try this again. These are referred to as index registers. So they had the ability to be loaded from memory and store values into memory. There weren't really instructions to do arithmetic on them, but they had this really powerful set of instructions that would let you use the X and Y registers to change the memory address that the accumulator was referencing. So you could generate code from, a compiler generating assembly language could do things like implement a for loop by having the loop counter be in the Y register, for instance. And then at the machine language level, if you were loading a value from memory into the accumulator, you could say, I want to do a load indexed by Y, and it would add the value of the Y register to that address for you. Very powerful idea. Very powerful idea. Then SP was the stack pointer. So something really cool about this type of machine language is that it actually had a machine implemented stack, which could be used for implementing functions. So there was a machine instruction that was a jump saving a return address. And so when you did the jump saving the return address, it would actually take the value from the program counter and store it at the memory location referenced by the stack pointer. And then it would increment the stack pointer by 1, thus doing a push onto the stack, all in circuitry. So you think back to data structures and you coded up a stack. On the 6502, they coded a stack in hardware. A really powerful idea. Of course, it meant that if you were going to do the jump, and we're going to be experiencing this around chapter 8 in this book, before you did the jump, you had to push all of your local variable values onto the stack so that they wouldn't get corrupted by the subroutine. And this is precisely what function calling looks like in almost any modern programming language. So typically to do a function call in this machine language, you would push a ton of stuff on the stack. Then you would do this special jump instruction that automatically pushed the program counter on the stack. It would go through its subroutine, and then it would hit a special return instruction that would load the program counter based on the value on the top of the stack. And then when you returned, you would then pull off the stack all of the local variables that you had been storing. So it took a lot of instructions to call a function but the hardware actually supported it in a way that this hack machine really doesn't. We'll be implementing all of that functionality in software as we get into chapters 7 and 8 of the book. So that gives you a feel for what programming on the 6502 was like. It was fun. I enjoyed it. But yeah, and it had memory mapped I/O, which was tremendous fun because for the time, the Commodore 64 I was programming had a pretty awesome graphics card. Like in the graphics card, it had hardware controlled sprites. So in other words, you would tell registers on the graphics card, look at this region of memory to see the bit pattern and coloration for a sprite I want to animate. And then entirely in hardware, you would instruct it how the sprite was supposed to move around. And you could have up to like 8 of them. It was pretty cool. It was really cool.
Question.
Yeah.
When you say in hardware, you could tell it how it's going to be animated.
Yeah.
You mean you're coding it in assembly language or machine language?
Oh, yeah. Yeah. So you would, because it's all memory mapped I/O, you would store values in memory locations that were mapped to the graphics card that would tell it how to move it. So essentially what you're saying is, you're telling the graphics card, I want this sprite with its upper left corner at this X coordinate and this Y coordinate. And it would put it there. And so you'd have data structures in your program tracking how you want it to move, right? So memory mapped input, you could actually plug a joystick straight into the Commodore 64. And then memory mapped input, you could read how the joystick was positioned by doing a memory read. So then you could write code that based on which way you pushed the joystick determined how you updated the positional registers on the graphics card to affect motion of the sprite. And so it was pretty easy to write a program in machine language where you would steer a sprite around using the joystick. Yeah. On a modern machine, we take care of a lot of those details. Well, it's a combination of hardware and software, really. But there we were. And I mean, on top of this, it also had an amazing sound chip, amazing for the time. So the sound chip had a 3-channel output, so you could play up to 3 independent melody lines simultaneously. And you would specify, it was actually a sound synthesizer. Again, just by storing data in memory that's been mapped to the sound card, which in turn was wired directly to the speaker, you would actually specify the complete waveform of the sound that you wanted. Yes? So there was, again, a register on the graphics card, memory mapped, where you specified what color you wanted when you were rendering something. So it could be as simple as, if I'm plotting a pixel, I want it to be a certain color, I would set that color register to specify the color, and then I would tell it to plot the pixel, and that pixel would appear in that color. So this machine's just strictly black and white, of course, but it's not too big a jump to imagine doing that. On a more modern machine, it's more typical that you've got multiple bits representing every pixel, specifically 32 bits per pixel. And so the way that we use those 32 bits is we've got 24 bits specifying the color and 8 bits specifying what's called the alpha value, which is how transparent is it relative to the background. How much of an underlying color might you let through, sort of a thing, from the background. So they set the background color as its own thing. And then the alpha value determines how much of that creeps through. And so what happens is, in a high-level language, you give it an API that lets you specify all that. But that API is ultimately compiled down to machine-level instructions that are just storing values in these memory-mapped registers. So what's great about the API is that when you're programming in a high-level language, you don't actually have to know where in memory you're doing these updates, which is good. which is good. And you also don't have to know what specific bit patterns to store in memory to get those updates to happen the way you want them to happen. The API takes care of that for you, and that API ultimately comes in the form of what's called a system call, which is a function call where you're asking the operating system kernel to do something for you. I get into more details on that distinction in my operating systems class, but that's the overall framework in which we can look at this. Does that make more sense of it? Cool. All right. Obviously, I could talk all day about the 6502, but I want to move on a bit and talk about some other very important processors that came along. Kind of the next wave, and here we're looking at pretty strictly the 80s at this point, was 16-bit CPUs. So by 16-bit, what we mean is that they had a 16-bit data bus. It wasn't too long before many of these 16-bit CPUs wound up having 32-bit address buses. So what are some major ones here? Well, first big one, the Intel 8088, which wound up in the first IBM PC. Whoops. So I got to tell you something that's insane. Every modern Intel CPU can run a machine language program that ran on the 8088 unchanged, and it'll work. Intel, even though they've added features to their CPUs as they've evolved over time, has maintained strict backwards compatibility with the 8088. So if you compiled a program in 1982 on an IBM PC and generated a binary from it, you could take that binary, run it on a modern Windows machine, and it would run. So the combination of IBM and Microsoft and Intel all work to, IBM's now actually out of the picture, actually. They no longer make PCs of any kind. But that combination of companies was determined to maintain backwards compatibility. Their customers were primarily business customers, and once that business customer had invested in some software, updating the hardware was not something that these companies wanted for their client businesses to have their operations disrupted. And so there we were. Another extremely important CPU during this time period was the Motorola 68000, and this was in the early Mac machines. So first Macs were about 1986 or thereabouts. This is so crazy. I'm talking about all of this stuff. For y'all, it's ancient history. For me, it's just memories. I was there. I had an early Mac. You know, I programmed the early IBMs in my high school. You know, that kind of a thing. Yeah. But now this is like, what, 15, 20 years before y'all were born? Wow, mind-blowing. Anyway. So these two CPUs were highly dominant in the mid to late 1980s. Highly dominant. The Intel family continued to evolve while maintaining backward compatibility. So as it evolved into more of a 32-bit family, we had the 8286, the 8386. So when we're talking 8386, now we're thinking about 1992 or thereabouts. So we're getting into the 90s now, slightly less ancient history, still before you're born. And then they kept incrementing that. So then they had the 8486. It's getting more and more sophisticated. For the time, this ran at something like an amazing, 80 megahertz. It's pretty awesome for the time. That Commodore 64, my first computer, ran at 1 megahertz. I got that computer in 1982. All of a decade later, we were 80 times faster. Think about it. It's nuts. Okay. And then finally, instead of calling it the 8586, they called it the Pentium. The Pentium. And then they stopped using those numbers, and they came up with, Pentium Pro, Pentium Plus, Pentium this, Pentium that, and all modern Intel processors continue to be direct lineal descendants of that Pentium series, which hit around 1995 or thereabouts. Okay. At the same time, there was a widespread sense that CPUs were getting too complicated. By the time we get to something like the 83, 86, the underlying machine language was absurd in its complexity. And figuring out how to actually design the circuit was becoming incredibly painful to continue to have a good throughput and so forth. So at this point came the notion of what was called a RISC machine. That stood for Reduced Instruction Set Computer. And the RISC chips first became popular in the CPUs produced by Sun Microsystems. So Sun workstations all had CPUs in what was called the SPARC family, which were examples of these RISC machines. So what distinguished them? Basically, the RISC machine was all about stepping back and saying, what's the minimum amount of stuff we need in a CPU to actually get it to do anything? Bearing in mind that at this point in history, humans hardly wrote any assembly language. The main writer of assembly language was a compiler by this point, okay? And so the RISC machines had some premises, including, one cycle instructions. There were and are Intel instructions that were going like 6 cycles, for instance, to execute. It was nuts. So these RISC machines insisted on a 1 cycle instruction. They wouldn't bother with a hardware stack. They would have instructions where you could change a lot of registers at once. That was another aspect of these, was huge numbers of registers, like say 32 and more. The Intel series, starting with the 8088, I think the 8088 was 8 registers. Some of the later ones pretty quickly went to 16 registers and so forth. But for the time, the RISC machines had huge numbers of registers. And that was something very distinctive about them. The primary ARM, or the primary RISC machine still in use today, is ARM. ARM is massive. What ARM did was identified a market niche. The Intel, and of course AMD cloned all the Intel processors and so forth. You can think of AMD and Intel as the same thing for this purposes of this discussion. They continue to be dominant on the desktop, but the ARM consortium recognized that the complexity of the circuitry of those CPUs actually wound up increasing the power drain. Like, it was just taking fundamentally more electricity to run programs with these things. And their insight was that the RISC concept enabled us to think differently about reducing the power consumption necessary. That in turn made ARM completely take over the embedded software space, embedded devices. Basically, every smartphone manufactured is sitting with an ARM CPU in it. That's obviously a dominant sphere, but when it comes to embedded, ARM is the absolute dominant CPU family. And that's a descendant of this RISC concept. In fact, ARM stands for Advanced RISC Machine. Because these people knew how to pick a name. If you're going to do an acronym, you better make it pronounceable and memorable. And then you also better make it brag. It's an Advanced RISC Machine. ARM, it connotes strength. power. Anyway, ARM is, the design is the intellectual property of a holding company that then licenses the design to manufacturers to actually create the chips. And so they're created by a lot of different companies, including Intel. Intel isn't exactly the kind of company to be left out of a game if they can help it. So for embedded, ARM is pretty dominant. It's become popular as well in certain laptops. Over time, Mac phased out the 68,000 and began adopting the Intel series. There was even an awkward time period where every Mac compiler would spit out basically 2 executables, depending on which CPU happened to be in your current Mac. That sort of thing. So this is just sort of a brief tour then of what the landscape generally looks like with modern CPUs. All of these, even something like ARM. ARM is pretty programmable. Intel, it sucks to write Intel assembly language. It's extremely unpleasant. ARM is actually kind of fun to do. But all of them come back around to the basic ideas we've explored in the last couple of chapters. Everything you do in a machine language is about changing the state of some kind of memory. You've got an ALU that does calculations that you can then feed into that memory state. All CPUs boil down to that. Some of them have some conveniences to make the process easier. ARM has this great bulk memory, modify 20 memory locations in one instruction kind of a thing. So in one clock cycle, you're modifying a whole bunch of stuff. And so, for instance, when you're doing function calling on an ARM machine, in one instruction, you can move all your local variables onto the stack and that kind of stuff, which is really pretty cool. But yeah, each one is its own jungle to navigate, but it all comes back to the same underlying principles, which I am sure all of you are developing a growing appreciation for. And then, yeah, memory mapped I/O. One thing that hasn't really come up here is what's called an interrupt. That is, you can have something that basically tells the CPU when this bit goes to a 1, stop your program counter, put it aside, and go do this other thing. And that's something I talk about in the operating systems class as well. So, cool. Any questions? Have a great time building your CPUs. As always, if you're stuck, come pay me a visit. I'll be happy to help.